Newton's third law is going to be the last law that we're going to cover. Newton's third law you'll often hear as, for every action there is an equal and opposite reaction, which is absolutely true. We're going to try to go a little bit more in depth in terms of what does that actually mean about the forces and how can we differentiate something that is showing Newton's third law versus something that is just a net force of zero. So first off, Newton's third law, forces come in pairs. Whenever there is one force, there is always a second. What's true about those forces is that they must be equal in size, they must be opposite in direction, but they also must act on different objects. A common mistake is that because objects have a net force of zero, people will say, well, those are action-reaction pairs. Take a car that is just sitting on a road, for instance, there are two forces acting on it. One force is the force of gravity acting down. A second force would be the earth pushing up on it as the normal force. Now in this situation, while these forces are equal in size and opposite in direction, they are not what are considered action-reaction pairs, or they do not show Newton's third law. The reason is because they are now acting on the same object. What we have to do is identify what are the other forces that are acting because of these. So let's look at the normal force. One instance of the normal force is we can kind of express it as what is happening. By saying that the normal force is the earth pushing up on the car, the pair to that, or the action that is equal to that, would be just the opposite of what that is saying, where we would say that's the car pushing down on the earth. So on the earth, there would be a force down, which would be the normal force due to the car. So for this, the normal force down would be the force that is the pair to the normal force up. And to understand this, we would just take this statement here and flip the nouns and change the direction, where we have the car pushes down on the earth. That is the action and the reaction, and that's a pair of Newton's third law. The other one here would be the force of gravity. Saying this would be the earth pulls down on the car. The reaction to that would be the car pulling up on the earth. Those are reaction and action pairs. Similar over here, where the idea is that Newton had an apple fall and that's how he discovered gravity, is the idea that if we have an apple that is falling downwards, it is falling downwards due to the force of gravity. That force of gravity has to have a pair. There has to be an additional force acting because of this. So what we could say is the earth pulls down on the apple. The reaction to that would the apple pulls up on the earth. Those two forces are opposite in directions, they're equal in sizes, as well as they're acting on different objects. And that's what indicates that they are Newton's third law. Now, because we know F equals ma, the idea behind Newton's third law is that while the forces might be exactly the same, their accelerations are going to be very different. And that's because they're difference of masses, right? The acceleration of the apple is going to be force over little mass, so it can have a big acceleration, whereas the acceleration of the earth is going to be insignificant. And that's because the Earth's mass is so much larger than the mass of the apple that if we take the force and divide by the mass of the Earth, we get a value that's so insignificant that it doesn't actually cause the Earth to move. You don't feel that, right? When we drop a marker, the marker gets pulled down and it accelerates. The Earth, while it technically accelerates upwards, it's such a small acceleration because the mass of the Earth is so big that we don't actually feel it. So let's see how Newton's third law comes into play here. And we're going to do an example looking at two blocks that are attached together by a string, and we're going to pull with a 50 Newton force to the right. Indicating the forces on each block, I'm going to say that there is the force of gravity on A, along with the force of gravity on B. It's going to be a smaller force because we have a smaller mass. Normal force on A, normal force on B. We're going to say this is a frictionless surface, just to simplify the problem. And then there's other forces that are acting here. So obviously we have the applied force of 50 newtons to the right. We have a tension force to the right on block A. And then we also have on B, we have a tension force back. And so what we're going to see is we're going to try to prove that this tension force and this tension force are exactly the same. Basically what that shows is B pulls on A A pulls on B, and those two forces need to be exactly the same. So how we're going to do that is we're going to work through the problem as a whole first, and then we're going to break it down into their individual pieces. So first we're going to work through the problem as the system of everything. So everything is at play here, right? So if we do that, the sum of the forces in the y direction are going to be the normal force on A minus the force of gravity on A plus the normal force on B minus the force of gravity on B equals mass times acceleration. My acceleration in the y direction is 0, so we know that all of these forces are going to cancel out. Normal force and gravity are the same, normal force and gravity are the same, so these really add up to 0. In the x direction then, what we're going to do is these are considered internal forces. And so we're going to ignore those because they're part of the system internally. They're not external forces that are happening. Gravity and the ground are external things acting on my system. And then this applied force is an external force. So we're just worried about the external force. So this is just my applied force equals, this is my mass total. So the mass of A plus the mass of B equals my acceleration in the x direction. We have an acceleration here because there's no other force that's going to balance it out. So let's solve for acceleration in the x direction. That's going to be my applied force divided by the sum of the masses. It's going to be 50 newtons divided by the sum of my masses, which is 15 kilograms. And I get an acceleration in the x direction of 3.33 meters per second squared. So here's what we know. Because that's true, we know that A and B should both be accelerating at the same rate. B is not going to accelerate any more than A, and A is not going to accelerate any more than B. So if we work through this system or this process again, just focusing on A and B, can we then use that to determine what the value of the tension force is? So let's look at the system for block A. I'm going to skip the gravitational force and my normal force because we already know that those are going to cancel each other out. So let's just focus on the forces in the x direction. So the sum of the forces in the x direction, that's going to be just my tension force. And that's going to equal the mass of A times the acceleration in the x direction, which we already solved for my acceleration, which is 3.33. So let's solve for tension. So tension force is going to equal the mass of A times the acceleration it's experiencing, 3.33. So what that tells me is that the tension force at A is 33.3 newtons. Now what we should see is when we do the same process for B, we should get a tension force that is exactly the same. What that's going to prove is that if A is pulling on B, B must be pulling on A with the exact same tension. So working through this process again, but now just with block B, again, we're going to ignore our y forces because those don't really matter. And now we're going to have these two forces here. My equation is going to look like my applied force, subtracting my tension force, equals mass of B times the acceleration we experience. Well, let's solve this for T. When I solve for T, T is going to equal my applied force minus my mass times the acceleration in the x direction. When I plug in my numbers in, I get 50 minus 16.6 when I multiply my mass times my acceleration, and that comes out to be 33.4 newtons. And because we were rounding, this is a third, that's also a third, we can see that those two tension forces are exactly the same. And so from that, we can prove that Newton's third law actually works out. That for every action, B pulling on A, that's what this tension force would be here, has an equal and opposite reaction. A pulling backwards on B. Notice those forces are acting on different objects. They are acting in opposite directions. However, they are the exact same size. So you'll see this at play through a lot of different problems. We typically do not deal with Newton's third law, but we have to understand how we can apply it. This setup of how we work through this type of problem is a great example of how we would work through an Atwood machine problem and why we would typically ignore the tension in between two blocks because we know the tensions are going to be exactly the same and they're part of the system, so we can ignore them when they're part of the system. When we're looking at just a single block, then we have to take them into account because they're no longer internal forces but external. But when they're within the system, they're internal forces, and so we wouldn't apply them to our force equations.